Hi, welcome to the class. Today we'll do one experiment on simple pendulum, and the objective of this experiment is to find out the time period of oscillation for a simple pendulum. And in this we will be changing the length of the string of the simple pendulum, and we will try to find out the time period of oscillation for that particular length of the thread, and then we'll try to establish a relation between the length and the time period of oscillation. So what we are going to do, as you could see, that this is a simple pendulum. So here you have a bob. So this is the bob and this is the thread, and this is the point at which this bob is being hanged. This is a stand. This is what we call the retard stand. So this is the retard stand. We need a scale also. Here is the scale and here is the stopwatch. So all these apparatus you need for this experiment. So what I am going to do, we all know we all know the name of the position where the pendulum is resting right now. I'll take it up to this point. You all know what this position is known as. It will go there, it will come back. The moment it comes back, I'll start the timer. Okay, so let us understand it. Time on. So the moment it will come back, I will start the time, and when it comes back again, I'll start the counting. So I'll be taking out the time period for 10 oscillations rather than for one oscillation, and then I'll convert it into time period for one oscillation after taking it for 10 oscillation. The reason being that in experiments we do some kind of error. So by taking a maximum oscillations, that is 10 oscillations, the error can be minimized. So let's begin the experiment. So right now the length is 25 centimeter. So I'll show you the data later on, that what we have done for 25 centimeter and all that stuff. So the data I'll show it to you later on. So let's begin the experiment. So I'll take it here, I'll release it, and then I'll start the watch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right now this is 25 centimeter and the time period is around 10.5. So the time period is around 10.5. So that is the time period. So this is for 10 oscillations. Time period for 10 oscillation is 10.5. So the time period for one oscillation will be 10.5 upon 10, that is 1.05. So I am taking it up to one decimal place only, so it will be 1.0, that is 1 second. So time period in this case is 1 second. Now I will make the length of the string to be 36. Now you must be wondering why I am taking 25, 36. So the reason is that I have taken the same readings which are given in your book. So let me do it for 36. So here you are. Right now the length is 36. So again I'll start the experiment. So let me take this pendulum to this position and start oscillating it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I did a mistake actually. Let me do it again. I did not note it properly. So these kind of errors takes place when you do experiment. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this time the time period is approximately for 36 it is 1, 11, 12. Yeah, so it is around 12.5. So it is around 12.5. So that is the time period here, 12.5, right? Time period is 12.5. So for 36, 10 oscillation time period is 12.5. For one oscillation it will be 1.25. So I am taking it up to one decimal place, that is 1.2. Now the length I'll make it as 49. So right now the length is 49. Let me begin the experiment again. I'll start oscillating it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for 49 it is approximately 14 seconds. So for 10 oscillation it is 14 seconds. So for one oscillation it will be 1.4 second. Now the next length I am going to take is 64. So this is the length 64. Again I will begin it by oscillating. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is coming around 16. So for 64 it is coming 16. So 64 it is coming 16. So that is 1.6, right? And now one more reading, I'll take it for 81. Let's do it for 81. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So guys, this is 16. It's coming like 19.5. So it is coming around 19.5. So 19.5 it is coming. So which will be 1.9, right? So this is the data. And I'll show you the data first. Then you try to conclude something based on this data. So I have written the data. So this is the data. So this is the observation table. Length is in centimeter 25, 36, 49, 64, 81. 100 I have not taken. Time period for 10 oscillations in seconds. Time period for 1 oscillation in second. This was time period for 1 oscillation when the length of the thread was 25. Time period was 10.5. As you could see, the length is increasing, the time period is also increasing. So can you establish a relation between the time period and the time period of oscillation and the length? Tell me, can you establish a relation? Yeah, so the relation is that as we increase the length of the thread, time period also increases. So this is the relation which we could establish. Now here I have calculated time period for one oscillation, dividing these time periods by 10, because these are the time period for 10 oscillations. When you do so, and then when you calculate L upon T square, this I'll tell you why we have calculated L upon T square, because we have to plot a graph of L versus T square. Graph of L versus T square we have to plot, and from that graph also we will get a information. So graph of L versus T square we have to plot. So I have calculated L upon T square for this. So T square means square of this time period. So if you take L is 25, T square means 1 square, that would be 25. L is 36, T square 1.2 square, 36 upon 1.2 squared, if you do, it will come 1.44. So 36 upon 1.44 will give you 25. Here also if you do 1.4 squared, that is 1.96. And if you divide it 49 by 1.96, that will give you 25. 64 divided by 1.6 squared, 1.6 squared, that is 2.56. If you do it, you will again get 25. So let's plot a graph of L versus T square. So I'll take all these values of L and all these, I'll square these values, and then I'll plot a graph between L and T square, right?